So this presentation is about Swerve pathfinding. First off, we're going to go over just regular PID pathing, where you have one place you want to start at and another place you want to end at, and you just go that way. And then the second half of this presentation is going to be about how you move around obstacles using an algorithm. So who am I? I'm a senior at Bronx Science. I've been on the Cyborgs for 3 years, and I'm the head of programming. I have a dog named Cookie. She's very cute, and I'm pretty decent at math and coding. Said this a bit earlier, but this presentation uses some vector arithmetic, so you might have a bit of trouble understanding what is going on if you don't know it. It's just adding vectors, subtracting vectors, on top of just scalar multiplication with how do you make a unit vector. And yeah, this presentation is very math heavy. For the simple PID pathing, I do briefly go over an implementation, a code example, but for the object-avoidant pathfinding, there will be more of just how do you get the final direction vector in order to move in that direction. So first we're going to start with PID pathing, just simple stuff, not object ignorant. It'll just go in one direction as fast as it can. So here is a profiled PID controller. We'll be working with one-dimensional profiled PIDs. You can consider it as a function of your previous positions, and it gives you, say, velocity or an acceleration, whatever. It just controls how fast your wheels are going. It will get you from one position to another position as fast as it can, and also be smooth. There's a maximum acceleration and a maximum velocity you can see on those graphs. It's an image I found on the internet. So first, if we want to get from A to B, just on a number line, for example. So let's say that our robot's position is x of t, it's a function of time, and our goal is a constant g, just a value. So we don't really care about where these are on the field as much as we care about where they are with respect to each other. So we're going to define the error function, e of t, as g minus x of t. So it's sort of, in this case, a one-dimensional vector from where the robot is to where the goal is. We'll feed this error into the PID controller to give it all the previous states, and it'll tell us the speed to send the motors and to move the robot to the goal. Now if we want to do this in 2D, we'll just take our x of t and turn it into a two-dimensional vector, for example. And then we will have our goal as a vector as well. You can imagine that this is on a field, for example. You have an x-coordinate. Usually that's the long side of the field, and then the y-coordinate, which is the short side of the field. If you know what I'm talking about. Does that make sense? Okay. And then there is our error function once again. So now if we want to do this in 2D, when we turn our error into a scalar, it removes all sense of direction. We take the norm, what we call it. And so since we only have a single-dimensional PID controller, what we actually want to do is we just want to take this norm of the displacement and feed that into the PID controller. Say that the output, for example, is mu. That's that symbol if you have not taken physics. So after we calculate this mu, all we actually care about is the direction of the vector. We want, as a result, a vector that has the direction of the displacement and has the length of mu, and that is what we want to set the motors to. We'll say mu is a speed for now. So that's what I just said, and mu times the unit of e is actually a velocity. So here we will have a robot that is going to accelerate in that direction. We'll normalize e, turn it into a unit vector, meaning it has a magnitude of 1, and then multiply it by mu, and there's our vector. We will have the robot, or actually all the wheels, go in that direction. So let's talk about some swerve kinematics. Yes?
In that previous approach of finding the direction and then multiplying it by your velocity, do you see that working better or worse than running a X profile PID controller and a Y profile controller and running those at the same time? Totally separate approach.
Well, that could also work. It is actually just a separate approach, and it's sort of a similar way of going about it. But the thing is, when you do that, sometimes your robot will finish getting to the Y position before it finishes getting to the X position. So if you want to really make sure that it gets there as quickly as possible, sometimes it's better to make sure that it's always going in the direction of the goal.
That makes sense. Thank you.
No problem. So swerve kinematics. If we want the robot to not rotate at all, just all of its motors going in one direction, that means that they should all be facing the same direction and going the same speed. So the entire robot, you could see, is going in that one direction. So then what we would do is we would also add some components to turn, because a swerve, of course, is able to turn while it's also translating. So we've already isolated the translation. Now just add the rotation and we'll be finished. So if we want to calculate what the components of the rotation would be on those modules, we would first plot our goal. There's our error. And if we want the robot to rotate in a circle, all of the wheels have to travel along that circle. Just imagine this in your head. A robot spinning in place. All of those modules would be tangential to that circle and be spinning in place. So, that cyan circle, the wheels will trace that path, and their directions will look like that. Does that make sense? Great. So there's our error function. That means all we have to do is multiply this by a separate rotational mu, and then we will get a bunch of vectors representing speeds for the motors that will travel along that circle. So that is similar to what you said. It's rather than doing X and Y separately, we're actually doing translation and rotation separately. So we have sort of a separate PID for the rotational PID. When we add these together, we get the desired rotation of the motors to the rotation and speed of the motors in order for the robot to translate that way and rotate that way, such that by the end of all of this happening, we will reach our goal both in translation and rotation. Try to imagine for a second what this would look like in your head. If you don't know, when you add two vectors, you put one, there's something called the tip-to-tail method. So you take the tail of one vector where it starts and just put it where another one ends. I'll pause here for a second. I don't want to go too fast. Okay. Have you imagined it? Well, it looks kind of freaky. It looks like that. Those are the resultants when you add all the vectors together. And if you think about it really hard, you can kind of see the robot kind of rotating and translating at the same time. But yeah, I actually also put the little pink lines. Those are actually that's the tip-to-tail method that I use to get these resultants. And so you can see that over a little period of time, the robot would actually move towards that goal, both in translation and rotation. And keep in mind that since mu is the output of the PID controller, as you get closer to the goal, it will eventually slow down to 0. That means that while this may be what the resultant vectors look like at this position specifically, as the robot changes positions, both in rotation and translation, they're going to change probably both in direction and in magnitude. So the direction of your wheels and how fast they're spinning is going to change as time goes on. Here's the code example I was talking about. This is where rotation and translation are handled separately. This uses WPILib vector class, actually. And so just like look at it, I guess. See if you can understand it. Let me know if you have any questions.
Mathmutual.angle modulus. That's just a modulus of negative 180 to 180. Is that what that does?
Yeah, it sort of clamps it down. That's so if there are any issues along the way, you don't have like a 370-degree angle and you don't go all the way around. So.
Is there a difference between pose.getRotation.getRadians minus the other rotation.getRadians rather than using the rotation.minus method? I think you can subtract rotations in there.
Yeah, I'm pretty sure you can. I guess it's just.
It would work the same both ways.
Yeah, it would work the same. I think this actually went through a few iterations, and that we did this method before we used angle modulus, and so we just decided that to keep the previous version because it does the same thing. Oh, yes.
Yes, I can see, but where are you fitting into the function? What's the parameter?
The parameter of this function?
Yeah.
It's a pose2D called target. So that is where you want to go. A pose2D has inside of it both a translation and a rotation. So that'll be a position on the field and a rotation of your robot on that field.
So like position like the aim attack and then your robot or something like that, right?
Yeah, sort of.
Okay.
Like if you were like a position of the robot when it's right up against the reef.
Oh.
It would have a rotation facing like into the reef, and also it would have like a position right against the reef. And so you'd feed that into it, and when you call this drive to command with the input of that position on the reef, it would sort of pathfind there, both in translation and rotation. Yes?
And that target is like the raw position. It's not like the difference between
Correct.
the robot?
That's the absolute position on the field.
Absolutely.
Does that clear stuff up? Great. Oh,
So the set chassis speeds, is that what's sort of, because on the Swerve module you have the drive motor and you have the angle motor, right? So
Yeah.
that's sort of what taking care of setting each separately in one command, if that makes sense?
yeah.
Okay.
Set chassis speeds, I think in this scenario, it has a velocity in the x direction, a velocity in the y direction, and then an omega, so an angular velocity. So the modules, I believe, will handle that themselves. You can just assume that this is like an ideal scenario where if you want a module to face a direction, it'll immediately snap to that direction, and if you want it to go to a certain speed, it immediately will. In reality, that's not the way it works, but just assume that you have modules that are perfect for now. And then this set chassis speeds method sort of just sets the x velocity, y velocity, and rotational velocity. Now I do actually have another, I have another example for you, and I have a question. So look at it for a bit, let's see what can answer it. Yes.
Velocities in 3D.
It is a 3D, but why?
Does it contain X, Y, and rotation?
It does. So in this scenario, I've turned the angle, the angular displacement, into an arc length so that I can use the translation controller on it instead of a separate rotational controller. So similarly to what I was talking about before, in this case, well, in the previous one, you could reach your angular goal before you were reaching your translational goal, or I guess depending on which one is larger, it could be vice versa. However, with this one, it'll optimize everything because it will make sure that you'll get to all of them in the same amount of time. Since you can think of it like a vector in 3 space, where you have your x, y, and then your arc length in order to get to your rotational goal. I don't know if I explained that correctly. Are there any questions? Yeah.
So in 3 dimensions, that would be the shortest length to get there. Is that always,
Correct.
in Swerve, is that guaranteed to be the shortest time?
Well, if you have if you're trying to,
I think it's
Sort
probably really
of.
close to where it probably doesn't matter.
it is probably very close, but it's also just a different way of doing it. I would say it's the shortest time because rather than like going full steam ahead on rotation and then going for your rotation, it sort of just makes sure that like it kind of it works in a different amount compared to like what your displacement is. So, well, both work.
Cool.
You can implement it however you'd like, but I guess this is just a separate implementation I just wanted to show.
Oh,
Yes.
so my question was, since the third space allows us to get the shortest way to get to that set point, like how exactly does it do it? Like, I don't necessarily see any like map that does like lets it know that that's the shortest way to get there. Like, where do we set that?
The shortest way to get there is like if you wanted to go from your start position directly to your end position, but what the difference here is that it treats your rotational displacement as an arc length for your wheel to travel along. So that's also a distance. What that means is that it will that your like say you had a very large angular displacement and a small translational one, your wheel would travel along that arc length from the angular displacement, and it would prioritize that because it is in the same it's in the same vector. So when you take the unit, when you normalize it, it will sort of have more weight on where like on what the wheel does. Yeah.
Is the PID variable a vector 3D? Like,
The PID variable here is it's a profile PID controller, but it is one-dimensional. So what we do is we actually take the norm of the displacement, or difference in this case, and then we feed that into the PID controller to like so that it will, and then afterwards we multiply that that output of the PID controller by the unit vector of the difference, so that it will travel along that way. But also we'll treat in this case like angular displacement as a distance for the wheel to travel along. Any other questions? Tell me if I'm not explaining this well. Okay. So now we're going to move on to object-avoidant pathfinding. So the algorithm that I'm going to be teaching in this presentation, it actually uses a vector field. At every point, it will calculate a direction, and then you can use the profile PID of your displacement in order to give you a speed as well. It's the same sort of thing as before, except we just have a different direction. So imagine that there was an obstacle right there. What would happen if I were to use the algorithm we just used, the simple PID pathing? Yes?
Essentially could go through the obstacle.
Yeah, it would go straight through. It would crash. Now, that's not good. We don't want it to do that. So, what we actually want is something that will go around obstacles. So we have two goals. We want it to first move towards the goal, and we also want it to move away from obstacles. So at any point along the curve, I meant its trajectory right there, we want to determine the velocity at which to set the motors to. But we already have that with the PID controller, with the trapezoid profile. So the majority of the time, since like we want to go at top speed unless we want to decelerate towards the goal, the majority of the time, all we actually care about is the direction at which we're traveling. Because if we were to travel, because before we were traveling just straight towards the goal, and we were crashing into an obstacle. But if we switch our direction to move around the obstacle, we'll still want to go top speed as long as we can to get there as fast as possible. Oh, and yeah, there's a note on the bottom. Rotation isn't that important in object avoidance because it's not very common that you will rotate into an obstacle. But so you can just like use that first method as we talked about before. Just rotate while you're pathing, and then this algorithm will just handle the translation. So first we're going to think of a method that involves a sum of forces. So we want a force towards the goal, and we want a force away from obstacles. And then when we sum them together, when we add them, we will get a resultant that gives us a direction that we want to travel. So if we're closer to an obstacle, it'll push us away from the obstacle. And if we're closer to the goal, well, we care about going to the goal more, so it'll push us towards the goal. Again, another note, this is not a Newtonian force. This is not F equals ma. This is just like a sort of, just an imaginary sort of force. So first, we want a force towards our goal and away from obstacles. We'll graph our displacement vectors. And yeah, the goal force. So we want a force that points towards our goal. We'll use the inverse square law, actually, which means that it'll be sort of proportional to 1 over the displacement squared. But we're going to add a little plus 1 right there, because as we get closer, as we get farther and farther away, we still want the goal force to be relevant. So the magnitude of the goal force will be 1 over the magnitude of the area squared plus 1 times a constant, which we will call the strength. This is something we can tune depending on, I guess, the obstacles around or the game or whatever. Yeah, the magnitude also will get larger and larger as the robot gets closer and closer to the goal. The reason is that there are probably less obstacles when you are 1 inch away from the goal, so you don't really care about moving around obstacles as much. So you'll just focus on going straight there if you are close to the goal. Now we want a force that goes away from obstacles. So this one is actually going by the inverse square law. So the magnitude will be the strength divided by the distance from the obstacle squared. I don't know if I said this before, but E, that's still the error function, and R is the distance from the obstacle. So we also want it to be in the opposite direction from the obstacle, though, because we want, when we add it, for the force to push us away from the obstacle, not push us towards it. So we will negate it to flip its direction, and then our obstacle force will end up being equal to this right here. So negative strength over the norm of R squared times the unit vector of R. That's what the little hat is for, if you don't know. And when we add these two together, we will get those. But tip to tail, and we'll get that. Now that looks pretty good. It looks like it's going to move us around the obstacle, which is exactly what we want, rather than going straight towards the goal. But now, what if I put us here? We're like, the obstacle is sort of right in between us and the goal. In that case, there's our resultant. Can someone see a problem here? Yes.
We are just driving way too far away from the obstacle. We are crashing towards the obstacle.
We're going to explode. We are going straight into the obstacle.
Okay.
And so that means that we need to go around obstacles as well. We don't want to just go away from them. We want to go around them. So let's introduce another sort of another force. We want it to be perpendicular to r, the displacement from the obstacle. We'll rotate it 90 degrees counterclockwise. You can do this with some linear algebra rotation matrices, or you can just think about it in your head and then implement it later. We'll call this new vector r perp, so just perpendicular to r. However, in this scenario specifically, the direction should be the opposite way, because the robot is closer to going around the other side of the circle. So, in that case, if we want to implement this in real code, first let's take the angle from R to E. This is clockwise rotation, so it's actually negative. And then we multiply by the sign, like positive or negative, of the sign, trigonometric sign of the angle. So that's a mouthful, but you multiply by the sign of the sign. If the angle is negative, r perp will be reflected the opposite way. And if the angle is positive, meaning you should have gone like clockwise around anyway, it'll be positive and it'll stay the same. The sine function, it's like signum. It's in the top right. It's positive if positive, 0 if 0, negative if negative. Pretty straightforward, just in case. So there's our formula of the tangential force. For now, we just set it at 1/2 of the obstacle force, the magnitude. Because we don't want it to truly overpower the obstacle force, but we also still want it to be significant. So our formula, like our vector formula, ends up being that whole mess. It's 1/2 the strength over r squared times the sine of the angle times r perp unit of r perp. So there's our tangential force. Here's our goal force. Here's our obstacle force. Oh, yeah?
So then we just have three forces and then all three equations combined help you go around it? Or?
Yes.
Okay.
So there are our forces. If we want to put them tip to tail, there is our resultant. So that is the direction the robot will travel in. And then we can just scale, take the unit of this, normalize it, and then multiply it by by the output of our PID controller. So the entire formula is right there. It's a pretty big formula, but there it is. Pretty interesting, huh? Now, if there are multiple obstacles, which there will commonly be, you can just add the obstacle and tangential force together. In that case, you just add them together for every single obstacle nearby. Of course, your goal force will stay the same because you can't really have multiple goals. And then it will just go around it. I don't think I mapped the vectors here, but you can just imagine that it'll probably go down and then around. Also, I actually forgot to say this. We abstract obstacles as circles, in this case. Circles in 2D space, because it's easier. It is very possible to make it hexagonal, for example, if you wanted a reef, but the error you'll get isn't really that crazy. And if you are like maybe half a meter away, it's probably better just to switch to regular PID pathing anyway, because it might be a little more consistent. So in that case, like when you're far away, a hexagon, a circle, they're basically the same thing. It probably doesn't really matter that much in the long run, though. Also, obstacles are not points. I was saying this earlier, they're circles, which means that actually you want to take your distance from the edge of the circle. But also your robot isn't a point either. So we're going to treat that as a circle as well. Let's say that we take these two distances. So you have the radius of the robot. So if you imagine the robot turning around, it can't leave that circle from its center. So it won't. So if the robot is inside that circle and the circle isn't intersecting with the obstacle, there will be no collisions. So radius of the robot and radius of the obstacle. So these two values of r should actually be replaced with the norm of r minus the robot radius minus the obstacle radius, because then you'll end up just with that value in between the outside of the robot and the obstacle, which is the one we actually care about. Does that make sense?
I have one question.
Yes.
The force that you're talking about, the vector of the obstacle, like where does it come from? How do we know how? Like, because we can kind of estimate what the robot's vectors are based on the velocity and all that stuff, but how do we do that for obstacle? Like how? Where does it come from?
So in general, you would do this with odometry, whether with simple wheel odometry, or maybe you incorporated some vision in there as well. So localization to figure out where your robot is on the field. This only covers static obstacles, so ones that don't move. In this case, say the reef, for example, the reef doesn't move. If you know where you are on the field, you will also be able to figure out beforehand where the reef is on the field, because it doesn't move. And then from there you can just... Ooh, spooky. You can then just figure out your displacement from where you are to where the obstacle is, based on, since you know where the obstacle is and you know where you are.
So essentially these constants are provided on the field.
Yeah, provided that you know where the reef is on the field, this algorithm is usable. Yeah?
If the obstacles were to be moving, would it just give you like discontinuous changes in like goal velocity or goal direction? It'll be interesting to test.
It would be interesting to test. I'm not sure. I think it just might not work as well. It just might not pathfind around them. I'm thinking of like, if you were to like add another component of the force, yet another component of the force that goes against like
Its velocity.
the velocity of itself and the goal, it would be very interesting.
What about moving goals? Would that?
I guess it'd be interesting to make.
Cool.
This presentation doesn't cover that, but
Full extension.
yeah. Yes?
So we know where we are and we know where the obstacles are. What if we have some parts of the field that we want to also avoid and treat them like obstacles? How we go about like implementing that? Like let's say create your own obstacle on the field and avoid that at all costs.
Like what? Like just have multiple obstacles. Is that what you're saying?
Like, not really. It's like, because like reef is it's physical, right? It's on the field, right? And one definitely avoid it because you don't want to crash into it. But let's say there's some part of the field, let's say an opposite alliance of the barge, right? You never want to go there, right? So like, how can you like go about implementing that obstacle like physically? So like, it's not about crashing into it, but just avoiding it essentially for the robot to never go there.
You could treat it sort of just the same thing as an obstacle. Oh. I guess you just treat it as another obstacle. It doesn't. These obstacles don't have to be physical to be incorporated into the algorithm. Say that there is just this one point on the field that you really, really didn't want to go near, just for the heck of not going near it. In that case, you could just say it's an obstacle, and then some forces from that will be incorporated into the algorithm, and then the robot will not go there. Yeah. And also, if you were to have an infinite straight wall obstacle, say that like the walls of the field, or maybe you didn't want to go to the opposite alliance, so you just have like an infinite straight line obstacle that goes like straight through the half field line. In that case, you would just treat R as the minimum distance from the robot to the distance from the robot to that obstacle. So in this case, you could just say like the robot's x coordinate would be the distance from the wall on that side. The y coordinate would be the distance from the robot to the bottom. You would end up just with a single obstacle force that would point opposite of it. Additionally, we don't need a tangential force because it is somewhat difficult to go around an infinite wall. So in that case, we just ignore it. We just want to go away from the wall. Oh yeah, and if you wanted to go, if you wanted like an infinite line obstacle on the top or on the right, for example, you just take the length minus x of t, the width minus y of t. So just use the components of your robot's position in order to figure out how far you are from those infinite walls. If you wanted them to be diagonal, it'd be a little bit more difficult, but you could still do it. You could just do some like some projection, like it's just a bunch of vector stuff. Yeah.
So if your goal is on the obstacle, like if I'm trying to score quality, does the magnitude of the goal force overwhelm the obstacle force, or do you switch to just like normal straight line PID once you're sufficiently close?
Well, in implementation, it's usually better to switch to PID when you're sufficiently close. But I feel like if you were to have an obstacle inside, like your goal inside of your obstacle, this algorithm realistically would still just like run into it. It's not made for obstacles inside of goals. It wouldn't like break your entire code or anything though. So here is our net force from that one situation we had before. We just removed the magnitude, so because all we cared about was the direction in the first place. Then we multiply by a translational mu, which is just still fed E of t. It's easier. You don't want to have to calculate an entire trajectory and then follow it. And then you just watch your driver lose their job. So you can see that the robot moved completely around the obstacle. No driver needed. You just hold down a button and it will try to go in that direction around the obstacle, in the direction of the sum of forces. If we want to add rotation, we do the exact same thing as before. We had some translational vectors representing the direction and speed we wanted the modules to go in order to translate. So all we need to do on top of that is add in vectors representing rotation, and although it won't like it'll just be it won't finish rotating at the same time it gets to the goal. It will still get to the goal in rotational translation, and that's what really matters. It won't crash into any obstacles. Yes.
So that just means we have the whole pathfinding algorithm just as translation gets you there. We're just putting rotation on top. Has nothing to do with the pathfinding algorithm.
Correct.
It just slaps on top.
Yeah, you just slap it on top.
Cool. Just to be clear, the pathfinding input. This is just an explanation of how pathfinding works, but the implementation is already done for us, right? And we just use the constants that are provided just to get there.
Actually, no. You have to implement this yourself. I have an example on our code base. You can just copy paste the code if you want. But honestly, I just care about how it works more than how we can use it, and so I made a presentation on the math behind how it works. If that makes sense.
But there is a demo if people could find this. Somewhere.
Yes, you could find this on the Cyborg's GitHub for our 2025 code. Do you have any questions? Yes.
So are you only utilizing, especially the second algorithm, are you only utilizing that during auto? Or
You can utilize it whenever. We do utilize it in auto because it has sort of a, as compared to pre-planned paths, we can actually have some feedback involved in case in case the robot trips on something. But if you wanted to have like very efficient pathing, and you didn't want the driver to have to drive around and then use a PID pathing to say align with the reef, then you could just have it. You just press a button. It goes over to the source, grabs a coral, and then you click another button, and it goes to the nearest unfilled reef, avoiding obstacles in the process. So you basically just reduce driving, well, assuming that there are no other robots in the way, to clicking 2 buttons, which I think is pretty cool.
Right, because my next question was going to be basically like, so that obstacle would be like a reef or something like that. So
Yes.
a fixed obstacle we have foreknowledge of, but the algorithm would not be robust against another robot.
Correct.
Right.
I'm sure that there are some things you could do in order to, well, assuming you know where the other robot is and what its velocity is, to account for those kinds of obstacles. But for now, the algorithm that I just showed you does not account for dynamic obstacles. Yes?
I mean, I guess a more robust algorithm would require you to know, if we want to account for moving obstacles, say, other robots, you would want to know their velocity. But could you just, every sort of tick of calculation, just say, oh, the obstacle has moved here, so just treat it like another static obstacle, and it would just have a separate position every time you move? Do you think that would work?
I do not think that would work.
Okay.
Because say that your goal was here, there's a robot here, and you're right here.
Yeah.
The robot will, in this case, try to pathfind around this guy, so the tangential force would move it this way. But if this robot is also moving this way, then you're just going to still crash into them anyway.
Gotcha.
So you'd have to account for their velocity, maybe even acceleration as well. Yes?
So, great presentation, by the way.
Thank you.
I wanted to ask, so this is one way of avoiding obstacles and pathfinding to a point. The other common way that you see is like using a library that implements a star, which generates a list of points, which then straight line for like paths to those points. Have you used both methods, and like, is there a benefit to using this obstacle avoidance PID over like a star?
Yeah, I prefer this over A star mostly because, I think I tried making an A star algorithm that used like a grid on the field, but it was very bad because the paths would end up looking like this, and that doesn't account for like speeding up or slowing down. So if you really wanted something that would take into account like the fact that you are on a continuous like 2D space, I think this algorithm is better. I guess you could also do something where you have like certain nodes on the field that are around the reef, and then you can just PID path when there's nothing in the way. That could also work. This is my favorite though because I love math. Did you have a question?
I was going to ask the same thing. It was about like Pathfinder's pathfinding command.
Oh, I tried using that. It was very bad. Have you ever looked at the Path Planner library?
Yeah.
That is genuinely one of the worst libraries I've ever seen in my entire life.
Oh, wow.
Me and Path Planner, we have beef.
Oh
my god.
What do you think about Choreo then?
Oh, I like Choreo.
No.
Yes?
So how would you factor in multiple obstacles? Would you just add in the forces from those obstacles as well, or?
Correct.
Okay. So I was just so instead of just multiplying it by the forces of for example the reef, right? That also factor in for example the wall or whatever?
Yes.
Okay.
So when you add all those together, you'll end up with a direction that will, I guess, prioritize the nearest obstacle due to it being proportional to 1 over the distance squared. And so as you get further away, it doesn't really care about those as much. But as you get closer, it will go away from those obstacles.
Okay.
Does that make sense?
Yeah.
What issues did you find in the Pathfinder library?
It is incomprehensible. I think I went to, I tried looking at their code for like trying to pathfind, and it included something where if it had an error, it would catch it and then try again. No, if there's an error, you fix the error. There should be no situation in which something like a pathfinding algorithm would error. It actually, you should look at it yourself. I don't have any like examples of why I hate it, but I'm somewhat not of a fan of the Pathfinder library.
I found like it had a couple of problems with pathfinding back in 2024, I think, during like the off season in Crescendo, because I was testing like the pathfinding. I don't know. It seems like in the 2025 version, it was better than 2024, but yeah. I don't know.
Maybe I should give it another chance then. I did not find it very easy to use. So if you can get it to work, great. You should use that. But for now, I like this method.
I was at a conference last week where people were giving talks on manually doing your Swerve calculations versus using obs, and manually doing pathfinding versus using the pathfinder. And the general consensus was that if you're using these libraries, if you plug them in and they work, great. If something doesn't work, their documentation is not great, their manual control over the low-level details is not great, so then it kind of just falls apart.
Yeah.
So plug it in and it works great. If not, you're out of luck.
Exactly, and I had multiple problems with PathPlanner when I was trying to use it.
You're doing all the calculations yourself. You can go and find the error because
Exactly.
you're controlling it all.
That's sort of what I think is a benefit to this as well.
Yeah.
Are you familiar with constrained trajectory optimization? It's basically the map they use for choreo, but in modern robotics, like that kind of on-the-fly optimization problem is used a lot. So I'm just curious what your thoughts on that is, because.
I have heard that choreo does have like optimized trajectories, but it is sort of it's not an algorithm that you would want to do 50 times a second.
This is true.
So that's why we use this instead. I feel like maybe with the new system core it could be possible, but for now on the Robo Rio this works pretty decently.
I think if you limit your step size, this is just, I'm just yapping about this, but if you limit your step size like really low, your paths are very discrete. But you can just use like some smoothing algorithm that have a really smooth path. But that's just something to mention. I think this is a very creative approach in my opinion.
Got it.
I just want to add to the Pathfinder hate. Like,
No.
so one of the biggest issues we had with the pathfinding was if you're like literally there's a check if your like set point is in some certain distance, if it's like really close, you literally will not attempt it.
Oh yeah,
So it was just the stupidest thing ever. And also we had issues where the first time we pathfind, your loop overruns would go like 3 seconds. Like that's like ridiculous.
We had the same exact issues with the tolerance where we would tell it to move to a set point, but it was really close. And although physically you look at it and it's like a very significant amount, like it's a big distance, but it still doesn't do it because it thinks that it's already there for some reason, and it just doesn't do it.
In the grid on the field, if your starting pose and the goal pose are in the same grid that you cut the whole field of it to, it won't even calculate it.
Yeah.
We just used the PID controls just to get it there, so we just didn't use pathfinding because it was a linear movement. So that's how we fixed it.
What it sounds like is we may be in the market for a new library. I don't want to put you on the spot here because I know you're a busy guy. But are there plans to publish this, perhaps?
Publish
Into-
this.
Publish the algorithm into some maybe separate package or repo or something, so separate from the 2025 robot code. Make it easier for
We
people.
want you to make a new library.
Exactly. Yeah, exactly.
I guess I might as well if there's enough demand for it, or one of you can since you know how it works now. But I guess I didn't have any plans to do that previous to this.
Start a Patreon. There you go.
Make money off of it.
Yeah, exactly.
Did you guys have a question? Yeah.
No, I think it's
Any other questions? Well, in that case.